Welcome to part 2 of the Overview of Patterns module. In part 1, we discussed the importance of design experience and leveraging recurring design structure in becoming a master software developer. In this part, we're going to introduce patterns as a means of improving software quality and developer productivity by mapping design problems to common solutions, identifying and naming recurring structures and behavior, conveying architectural knowledge, codifying design expertise, and enabling systematic reuse. We're also going to talk about some of the common characteristics of patterns. So what's the key to mastery? Well, as we talked about in the previous part, you've got to know programming languages. It's important to understand algorithms and data structures, but you need to go to the next step. You need to be able to find a way to be able to capture design experience in a way that you can apply to the projects you're developing and you can use effectively to communicate to your colleagues who you work with. So what's a pattern? A pattern is basically a solution to a problem that occurs within a particular context. And we're going to discuss many different aspects of that definition and enhance it and augment it a bit. But it's a nice place to start. As it turns out, the context can be various things. The context could be a particular programming language. The context could be a particular operating environment. A context could be a particular domain. And one of the key themes we'll see is that there's many, many different domains over which patterns apply. Patterns are important in the aerospace domain, where timeliness properties are crucial, where the right answer delivered too late becomes the wrong answer. Similar characteristics apply in other domains, automotive, various kinds of electronic trading. In the mobile device domain, for things like smartphones and tablets, it's important to have patterns that can work with constrained memory environments and power-constrained environments. It's also important to realize that patterns aren't just for software. It's beyond the scope of this course to go into the details, but if you take a look at the patterns literature, you'll find patterns describing building architectures, you'll find patterns that deal with civil engineering, you'll find patterns dealing with many, many things, including even playing chess. It's quite a rich and vibrant area of study. So what do we do? How do patterns actually describe these common solutions to problems in a particular context? Well, the first thing that they do is they start by naming a recurring design structure. Here's an example. This structure we're looking at here, which will unfold a bit over the next few slides, is actually something called the observer pattern. The intent of the observer pattern is to define a one-to-many dependency between objects so that when one object changes state, all the dependents are notified and updated. And if you look at this diagram, you can basically get a sense of the rough structure. There's something called a subject, and it's related somehow to something called an observer, and that's related to something called a concrete observer. And that's the basic sort of picture you should keep in the back of your head when you think about the observer pattern. But of course, we need more details than just the name and the basic structure. We need to specify the design structure more explicitly. And we do that by identifying key object and class roles and relationships, dependencies, interactions, and conventions. So take a look at the structure that's unfolded here. You can see now a bit more detail. You can see that the observer is an abstract class that has an update method. And you can subclass from this abstract class, and you can override that update method using the magic of dynamic binding and virtual functions and so on, so that you can have that method called through a pointer or reference to the base instance of the observer. You can also see that there are dependencies and interactions between the observer hierarchy and the subject. The subject essentially keeps a collection of observers, which it can store in various ways. It could store them in a linked list. It could store them in an array or a table. Doesn't really matter from the point of view of the pattern description. There's just some way of being able to keep those dependencies stored someplace. There's also various interaction modes. When you want to be notified that something changes, you register an observer, or more specifically a concrete observer, with the subject by attaching it. You can attach a number of these different observers, and then when something happens, when state changes, somebody invokes the notify method on the subject, and it turns around and calls back the update methods on all the observers. There are also some conventions here. One of the conventions is you probably shouldn't block for any length of time in a callback on the observer. Otherwise, you'll starve other observers and prevent them from doing their processing. Now, it's important to remember when we talk about classes and objects, we're being somewhat abstract. So think about these things in a loose manner. They don't have to be Java or C++ classes. They could be C structs. They could be C functions. You can apply patterns to both object-oriented and non-object-oriented languages alike. And we'll come back and talk more about that later. Patterns also abstract away from concrete design elements, the problem domain, the form factor, the vendor. So for example, we can apply the observer pattern, and the observer pattern has been applied many times, to different form factors, to smartphones, to tablets, to desktops, to laptops, and other types of user interface-oriented activities. They also, of course, are in different problem domains. You can apply them for user interfaces. You can apply them for avionics, mission computing, and many other things in between. And of course, they're independent of a particular vendor. You can have the implementation of the observer pattern in Android. You can have the implementation of the observer pattern in something like iOS. Doesn't really matter. The pattern is still crucial and important and very common. Patterns also distill and codify knowledge gleaned by experts from their successful design experiences. Patterns like observer didn't just materialize out of thin air. They were discovered over many generations of people who were trying to solve problems in particular contexts. For example, if you go back and look at the classic work on Smalltalk with their model view controller paradigm, you'll see that the observer is actually a portion of model view controller. It's basically the model and the view portion. So the observer pattern grew from experiences with languages like Smalltalk and other languages that built in those user interaction paradigms into the way the class libraries and the language itself was implemented. But observer has also been used in other places as well. For example, the ToolTalk tool integration framework that was developed by Sun in the late 80s also used observer heavily to be able to inform different parts of a tool environment when data changed and be able to disseminate that both across different processes on a workstation as well as across workstations in a local area network environment. So these patterns grew out of a successful experience that people applied. There's a number of common characteristics to patterns. One of the important ones, which we'll come back to a number of times throughout this course, is the fact that patterns are independent of programming language and implementation technique. By and large, patterns can be applied, the same patterns can be applied in Java, C++, Objective-C, C, Ada, you name it, Python, the list goes on and on. You'll find examples of observer patterns in almost all of those languages. There are, of course, certain patterns that are specific to a particular language or to a particular environment. For example, C++ has a language feature called destructors. And there's a whole variety of common C++ patterns, which we typically refer to as idioms. Language-specific patterns are called idioms, that take advantage of C++'s constructors to do various kinds of idiomatic behaviors and structures, such as resource acquisition is initialization, which is an idiom for grabbing an object in a constructor and releasing the object in the destructor to make sure you don't leak resources and to make sure that blocks are entered and exited appropriately with respect to things like error handling and exception handling and so forth. Patterns are also characterized by microarchitectures. This is where the recurring design structures come from. For example, if you take a look at the canonical view of the observer pattern shown here, you'll see that it has three main parts, three main roles: the subject, the abstract observer, and the concrete observer. And this is part of the microarchitecture. Most design patterns you're likely to run across typically have between 3 to 5 roles that they describe and demonstrate structurally. If you start getting more than that amount, you're either talking about an architectural pattern, which might have maybe 5 to 8 or so roles. And if it gets much beyond that, you're probably not talking about a pattern anymore. You're actually talking about a set of relationships between patterns, things like a pattern sequence or a pattern language, which we'll cover later in the course. It's also important to remember that these microarchitectures, and especially the visualizations of these microarchitectures, are really meant to be heuristics. They're not meant to be Procrustean structures that force you to always do things in one way and only one way. And we'll talk about this a lot more as we get further along in the discussion here. And you'll see that there's actually quite a range of variability in pattern structures. And a good designer learns how to use that variation to their advantage in order to tailor the pattern to their particular context and their particular use cases. Because patterns aren't code or even concrete designs, they have to be reified or instantiated and applied in particular programming languages. This is where things get really fun. So let's take a quick look at a snippet of an example of the observer pattern implemented in Java. In fact, there are pieces that are already part of the standard Java development kit. There's an observer class, and there's an observable class that's part of Java. So we might define something called an event handler that extends observer and has a method called update that gets called back when things change. We might have an event source that inherits from observable and implements runnable, which is a way of being able to run things in multiple threads in Java. And this would be connected to some kind of event source like a socket or a file or a terminal or a touch screen or something. And when things happen and state changes in a separate thread of control, this event source will notify the observers, which causes their update methods to be called. And then we can also go ahead and define just a very small snippet of some programs where you create a new event source, create a new event handler, and then go ahead and add the observer. You add the event handler to the event source, create a thread that's connected to the event source, and start the thread. And at that point, the observer pattern starts to run, and the control flow is called back automatically through the use of the interactions between the pattern components. So that's one way we could do it in Java. Doing the same sorts of thing in C++ is almost identical. We have an event handler class. We have an event source class. In this particular case, we're going to use some bits and pieces of ACE. So we can have some tasks, which is the way we do this in ACE. So you create a task, and you activate the task, and that does something very similar to starting a thread in Java. And this example, which again is just a small snippet, also illustrates the use of another pattern from the Gang of Four book called the bridge pattern. And we can use bridge in conjunction with reference counting to hide a lot of the details of memory management in a language like C++ that does not provide garbage collection out of the box. It's important to also realize that patterns aren't methods. They are adjuncts to methods. They're kind of like a flavor enhancer that you add to your food to make it taste better. You wouldn't eat garlic salt by itself, but when you put the garlic salt on the food, it makes the food tastier. So is it with patterns. You don't replace a method like the rational unified process or various agile methods like Scrum or Kanban with pattern methods. Instead, when you do various parts of the design of your software in those methods, you can use patterns to try to capture the recurring design and the recurring structure and behavior more effectively so people can learn from them and not have to repeat the same mistakes that people might have made in the past. It's also worth noting that patterns can be applied to more things than simply software design. For example, there's a nice body of literature that talks about patterns for organizing teams. In fact, there's even books on patterns for organizing agile teams, how to make agile teams more effective through the use of patterns for organizing the roles and relationships between developers and scrum masters and clients and so on. And believe it or not, there are even patterns for navigating other complex settings, such as the dating scene. There's a book called Dating Design Patterns. So you can find patterns on many, many things these days, not just on software design. If you take a look at the pattern literature, you'll notice that there's a number of different ways people describe patterns. One of the classic ways of doing things, which goes back to the mid-70s and late 70s, is something that's called the Alexandrian form. And this is based on the groundbreaking building architecture work by Christopher Alexander, who spent a lot of time capturing patterns for buildings. And his form tends to be fairly textural, uses a lot of italicized and bold-faced words to draw attention to various ways of trying to build more livable structures that provide people with shelter space help make the environments and homes and cities they live and work in more accommodating, more friendly, easier to live in. In the patterns community, there's a number of other forms as well. There's the so-called Gang of Four style. There's the so-called POSA style. There's a whole variety of different styles. These styles are characterized by some things in common. They all typically provide a name, a pithy name, a name that you can remember easily, such as adapter, or proxy, or reactor. And they also provide a brief description of the intent of what the pattern is trying to do. For example, the intent of the adapter pattern is to allow software components that weren't developed with knowledge of each other to work together effectively. Pattern descriptions also typically describe what problems are being addressed, describing the forces, the constraints on the design, the applicability, when to apply this pattern. These are very important because when you are looking through literature on patterns, you're often trying to find matches for the things you're doing with what the pattern is able to do. What kinds of problems do you have in your software? Can you find patterns in the literature that are trying to solve the same kind of problems? Those are good ways of matching problems to the domain in which you're trying to work, the context in which you're trying to apply them. And of course, patterns also provide a description of the solution. Most software design patterns tend to focus on visualization of the solution in terms of some kind of structure diagram and perhaps a sequence or interaction diagram that shows how the various participants in the structure interact with each other in canonical ways. Some other forms of patterns tend to de-emphasize the visual part and just provide you with a text-based description. Some have both. All are valid. What's important to remember here, though, is that the structure that's used to describe the pattern is just that. It's a description. It's not the canonical embodiment or the only way of looking at the pattern. And one of the things we'll see later as we get more into the course is that patterns can be realized and implemented in millions of different ways, sometimes in ways that don't even look at first glance like the pattern description in the book, and yet they still embody the same design structure and behavior. So keep that in mind as we go a little further. Various patterns also have additional descriptive parts than just these 3 or 4 main ones we've discussed. For example, many patterns give you some concrete examples to anchor the pattern and ground it in something that might be representative of what you're trying to solve. They may also oftentimes provide implementation guidance, giving you various tips on how to implement the pattern. What are the trade-offs in the implementation space? Provide you with some code snippets in languages like Smalltalk or Java or C++ or even C to demonstrate how the pattern might be applied. I tend to find those very helpful because it allows me to get a more concrete view of how the pattern applies in real life. Many patterns also describe the consequences, their pros and cons. Patterns aren't good in every situation. Sometimes you can apply them effectively, sometimes in some environments, but if you were to try to do them in different environments with different forces or different constraints, you would find that they had all kinds of problems. And we'll talk a lot about that as we go through the course as well. It's also very important to be able to demonstrate multiple known uses. In fact, a design is really not considered a pattern unless you can identify at least 3 different known uses from authors other than the people who are describing the pattern in a literary form. So the concept of the rule of 3 is very important. So patterns describe to you other things. In fact, many patterns also, pattern descriptions, give you human known uses of patterns. So you can see how they apply to something more than just the software domain. Another thing you'll often find in pattern descriptions is a notion of which patterns are related to this pattern. This goes back to the whole discussion of pattern sequences and pattern languages and pattern relationships. Patterns very rarely exist in isolation. Standalone patterns are rare. We learn about patterns perhaps individually, but when we use them, they go together in various forms. And so the known uses section is important to demonstrate which patterns are often connected together, as well as to identify what are some of the common trade-offs. Some patterns get used better in different circumstances. And so by describing these in a pattern description, it helps people to apply them more effectively. If you take a look at this URL, you'll see that there's actually a wide variety of other pattern forms that are worth understanding. But these are some of the ones that are most common. So to summarize this part of the module, overview of patterns, patterns support design at a more abstract level than source code. They help to describe the design as the design, as opposed to getting mixed up in relatively low-level and tedious and obscure language features. For example, you can talk about the observer pattern and think about it totally in a language-independent way without having to be concerned as to whether the subject keeps track of the observers as a linked list or an array or some other type of container. That design decision, that implementation detail can be left for later. Patterns also allow us to treat design as a cohesive unit. Once you understand the structure and interactions of the observer pattern, you can use that as a concept when you discuss with your teammates what are the right choices to make in your software designs. Patterns are also very effective as a target for design and implementation refactoring. Many people have legacy systems that may not have originally been designed with patterns in mind explicitly, but you can refactor the software with knowledge of patterns in order to make them more appropriate, more reusable, more extensible in the future. I worked on a number of projects in the mid-90s doing avionics mission computing, where people had a lot of legacy code written in a very tightly coupled, globally oriented Blackboard-like architecture with cyclic executives and so on. And we spent a lot of time refactoring that code to use patterns like observer and related patterns like publisher-subscriber to make it more modular, more reusable, easier to expand and contract. We'll talk more about that later in the class. We've been focusing predominantly in this course so far about patterns of detailed design and implementation. But it's important to realize that you can apply patterns to many other parts of the software lifecycle. You can apply them to the analysis phase. You can apply them to the optimization phase. There's patterns for how to optimize software effectively. You can apply them to testing and documentation, reuse, refactoring, and so on. We'll touch on many of those different topics throughout the course, but be aware that patterns are a wide spectrum approach that can make many things better, not just the software design and implementation. And finally, it's important to remember that even though people often equate patterns with object-oriented languages, that they can be applied to non-object-oriented languages as well. In fact, in my experience, developers who are programming in non-object-oriented languages like C are actually the ones who benefit the most from knowledge of patterns, because the language features themselves often don't constrain you to follow any particular design. So the knowledge of patterns can help to make it easier to read the code and maintain and evolve the code, even though it's written in a non-object-oriented language.